Hi, welcome to the Olympiad geometry. Let's continue our study on Orthocenter. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. So here is the problem. H is the orthocenter of acute triangle ABC. AP, AQ are the tangent lines from A to the circle with diameter BC. PQ are tangent points. Prove that PHQ are collinear. So for this figure, it's a very classic figure. Based on this figure, I think I've seen IMO problem, CMO problem, and some other computations. So this is a figure that we will discuss a lot. The first thing that we want to have an idea here for this particular problem is that there are many solutions for this problem, and the most simple solution or most elegant solution, I believe, is to use a geometry transformation. But we are not going to use that one because that would be a very important topic, and I don't want to touch on that before we systematically introduce that one. So we will just hold the geometry transformation method here, and we want to find other ways to prove. And here I think I figured out a way that I feel is most elegant way that I can think of to do the proof of this problem. And beyond that, I want to have a brief introduction for this figure and show you the possibility of this figure, how many problems can be introduced by this figure. Okay, let's just think about this problem first. The problem is asking us to prove that PHQ are collinear. So the first thing that we can think of that what is a P point, what is a Q point? They are tangent points, right? So we can think of connect the, let's call this is O, connect the OP and OQ. But would that be helpful with proving PHQ to be collinear? We don't know. So let's just redraw the figure again. But before that, we want to have an idea that because BC is a diameter of the circle O, that means angle BFC is 90 degrees, angle BEC is 90 degrees, which means that CF, notice that F and E are the interaction point of ABAC to the circle O, right? And also CFBE as the altitude, which means that the intersection point of the B and CF is orthocenter of triangle ABC, right? Okay, so for the next figure, I will not draw the CFBE. Okay, so let's find the BC here first, and then consider this as a tangent line, and consider this as a tangent line. Okay, this is P, this is Q, and here is O, this is A. Let's just consider about this figure first, right? Because AP equals to AQ, right? They both are the tangent line of the circle O. So we know that if we connect AO should be perpendicular with PQ, right? this is F, this is E. So based on this one, we have that, let's connect the OP, and we know that AO is perpendicular with PQ, right? And this point would be the midpoint of the PQ, so let's call it T. And based on this, we know that AP squared equals to AF times AB equals to AE times AC equals to AQ squared, right? That's the power of A to the circle O. And because OP is perpendicular with AP and PT is perpendicular with AO, so in right triangle APO, PT is altitude on AO, right? So we know that triangle AOP is similar to triangle APT and similar to triangle POT, right? And from this, the triangle AOP is similar to triangle APT. We know that AO to AP, right? AO to AP equals to AP to AT, which means AP squared equals to AO times AT. And we already know that AP squared equals to AF times AB equals to AE times AC. That means AO or AT times AO, AT times AO equals to AF times AB equals to AE times AC. That means FTOB, these 4 points are cyclic, right? And also ETOC are cyclic, right? So let's just connect them. We know that FTOB are cyclic and ETOC are cyclic, right? Because FTOB, this is cyclic quadrilateral, so we know that angle AFT equals to angle TOB, right? This angle equals to this angle. And because ETOC is a cyclic quadrilateral, so we know that angle AET equals to angle TOC, right? This angle equals to this angle. And because angle TOB plus angle TOC equals to 180 degree, that means angle AFT plus angle AET equals to 180 degree, right? And that means AFTE, these 4 points are cyclic, right? AFTE are cyclic. And if we look at the original figure, we know that CF is perpendicular with AB, BE is perpendicular with AC, so AFHE are cyclic, right? AFHE are cyclic. And these two means that AFTHE are cyclic, right? AFTHE are cyclic. So T is a midpoint of PQ, right? And now think about this circle, because they are cyclic, right? So the circumcircle of AFTHE has a diameter of AH, right? Because the circular angle of chord AH is angle AFH, which is 90 degree, which means that AH is a diameter. And AH is diameter. Right, AH is the diameter. And we already know that AFTHE are cyclic. That means angle ATH equals to 90 degrees, right? And we already know that angle ATQ equals to 90 degrees, right? Because AT is perpendicular with PQ. So angle ATQ is 90 degrees and angle ATH is 90 degrees, right? That means H is on the line TQ, which means that H is on the line PQ, which means that PHQ are collinear. Right. So for this problem, we didn't go direct to find the relation between P, Q, and H. Right. The first thing is that we check on the property of the tangent line and the relation of the tangent line BC and the center O, right, midpoint of the BC O. And then we find that FTOB, ETOC, AFTE are all cyclic quadrilaterals. And based on that, we find that the angle AT, based on that, we actually find that AFTHE are cyclic, right? And we know that angle ATQ is 90 degree angle, that means, and also angle ATH is 90 degrees. That means HTHQ are collinear, which means PTHQ are collinear, right? So this problem itself is from CMO training exam. Okay, it's not a very easy problem. But there are more interesting problems or more difficult problems from this one. For example, we've seen that PQ as a tangent point, right? So actually, if I connect P to C and I connect B to Q, you actually can prove that PC, BQ, AD are concurrent, right? And similarly, if you can also prove that PE, FQ, and AD are concurrent, right? The intersection points are always on the line AD. And even though you can do this, you can just find the projection of the F to BC, projection of the E to BC, and you can prove that this connection and this connection, they're concurrent on AD. Right? This problem can make it very, very complicated and kind of like analysis of the lines. And I think the easiest way to do those proof is geometry transformation, which we will leave it later. And actually, I would introduce a geometry transformation in a very systematic way, which may last for several years. We will do a short introduction first, and then we will describe about it later. I think I will make a new series of the or new playlist for the geometry transformation only, right? But that's it. This problem is an interesting problem. I hope you like this video. See you in next one. Thank you.